Okay, welcome to day two. Let's continue picking up where we left off on Tuesday. I'd like to say a couple of things before I get back to this. First of all, a few people have asked me if they are on the wait list, whether it's possible that they can be registered in the course. Now, the professors are absolutely forbidden from trying to tinker with the wait list. We get slapped if we try to do that. But I am told that people are continuing to be added to the course through tomorrow. So if you are someone who's on the wait list, it is possible that you will be officially registered tomorrow sometime. I've also received various questions about homework partners and more detail about the group project, etc. The first homework is such that you really have to do that more or less by yourself, and then when you're done, you will compare what you've done with a partner. Since people are still being added to the course through tomorrow, though, I haven't yet assigned partners for everybody for the first homework. I will do that over the next day or so. So you will have a homework partner soon. And I also will be producing a lot more information about the group project over the course of the next couple of days. So you'll have a better understanding of what that's all about shortly. Does anybody have any questions before I plunge back into Python? Okay. So, I'd like to very hastily review what it is that we talked about on Tuesday. We saw that in Python, you can create a variable by assigning a value to it with a single equal sign. And so here on slide 7, we created 4 variables referring to values of 4 different data types. A refers to an integer value, 123. X refers to a float, 2.7, S refers to a string, high, and B refers to a bool, true. Now, these values are all stored in memory somewhere in your system, and these variables are referring to where those things are located in memory. If I do something like creating A to refer to 123, that means that 123 is some data stored somewhere in memory. If I then change A to refer to something else, 123 is sitting there in memory with nothing referring to it any longer, and so it's reclaimed. It's what's called garbage collected, so that that storage can be reused for something else later. I think I mentioned that or something like that, but I may be mistaken, so I wanted to be sure to mention that again. Unlike languages such as C++ and Java, variable names do not have data types directly associated with them. It is the objects that you're interacting with that have data types, and variables just refer to those objects. So it's perfectly fine in Python for I to start out referring to an int and then change I to refer to a float, and then change I to refer to a boolean, and change I to refer to a string. Each time you say I get something, that modifies the variable I to refer to that new thing. And these older things that I used to refer to, so here I was referring to 123. 123 is in memory. When I say I gets 123.456, well, that changes I to refer to something else, and so that 123 is now gone from memory. Likewise, when I say I gets false, this 123.456 is gone from memory, etc. We looked at the 6 low-level scalar types that we're going to care about. There are a couple other more obscure ones that I won't get into. We talked about the arithmetic operators and their behavior and precedence and associativity rules. And we introduced strings And I showed you that in terms of introducing string literals into your program, Python actually allows 4 different notations. You can use either a pair of single quotes around your string, or a pair of double quotes around your string, or triple single quotes, or triple double quotes. Any of those will work equivalently to each other. The advantage of the triple single quotes and triple double quotes are that this makes it very easy for you to define strings that are multiple lines long. Whereas with the single quotes or the double quotes, you would have to, in order to create something that's multiple lines long, you would have to manually type in the \n where you wanted the line breaks to be. Everybody happy so far? Any questions? All right. Let's see. We have assignment operators, which you can live without, but they're convenient. And we got started looking at collections, specifically the list data type, which is sort of like an array in Python. I'm sorry. Well, it's sort of like an array in Java or C++, except that a list in Python can grow and shrink. We looked at using square brackets to create and also do subscripting into lists. We also looked at using named methods to interact with and manipulate the items contained within a list. All right, so if I start out with some list M containing 5, 2, 5, 9, 11, we know that we can access an individual item in there by using its index. So M sub 0 is a 5. M sub -1 is always going to be the last item, so in this case it's an 11. And I can say things like M dot append a 3 and M dot insert at position sub 3 a -4, let's say. And so I have a lot of flexibility and simplicity about creating and interacting with lists. And that's where we finished up. Everybody good up to there? Okay. Well, next we need to talk about this ugly distinction in Python between logical lines, which contain statements of code, versus physical lines, which are, what you type and then you hit the enter key. So you type some stuff and hit the enter key, and that creates a physical line. Now, typically, a short logical line will occupy a single physical line. So if I say x gets 12 and press the enter key, that x gets 12 is both a logical line containing a statement that creates a variable x and causes x to refer to the integer value 12. And it's also a physical line because I just typed x space gets space 12 and hit the enter key. But it is possible to have logical lines that are quite long and that need to be split across multiple physical lines. And this is a nuisance in Python. For example, if I say x gets, and I want to type my value on the next line down, in Python, if I press the enter key at this point, I get yelled at and told, no, that's not allowed. In order to continue this logical line onto a second physical line, one way I can do that is by pressing the / key right before I hit the enter key. And Python will act as though the / and the enter are sort of not there at all. So if I now say 345, that's fine. I've got one logical line that I've typed on two physical lines by using the / enter trick. And so x is now equal to 345. Another way of splitting a logical line across multiple physical lines is to enclose things in parentheses or square brackets or curly braces. We've seen that you can use parentheses to override precedence in arithmetic. Oh, this is not a good sign. I'm coughing 10 minutes into the class. All right, so if I say x gets parenthesis and hit the enter key, now Python is happy because I'm typing this logical line using parentheses, and I can just type 345 and use a closing parenthesis, and that works okay. I can also say, 5 plus 17, close parenthesis. And as long as I have my opening parenthesis followed by some sort of valid notation followed by a closing parenthesis, this also works fine. Here I've typed a single logical line across 5 physical lines by using the parenthesis trick. The same thing is true for lists using square brackets. I can say n gets, and then my open square bracket, 12, comma, 44, comma, 98. And there's a closed square bracket, and that's fine too. So that's obviously very convenient if you have a really long list of values that you need to type in. You can just type the first 10 or so and then hit the enter key and type the next 10 and so on, and that works fine. So far, so good. So as a consequence of this, in order to avoid having to remember to use the backslash at the end of a line, many Python programmers will just sort of automatically put arithmetic computations inside a pair of parentheses, because then you can just keep typing until you're done, and you don't need to worry about backslash enter at the ends of your lines. All right, so we've taken a look at how to separate a single logical line across multiple physical lines. It turns out you can go the other way as well. You can put multiple logical lines into a single physical line by separating the logical lines from each other using semicolon characters. In Java and C++, we're used to using a semicolon as the statement terminator character. In Python, semicolon is a statement separator character, and you can use it if you want to have multiple statements on a single physical line. So saying A gets 4, semicolon, B gets 13, semicolon, D, C gets 43 is just, lets me compress those 3 assignments onto a single line. Now in practice, what you tend to observe is that people don't do that. There's not a premium on writing compact code in Python, so people tend to just do one statement per line. But you can separate multiple statements in logical lines on a single physical line by separating with semicolons. All right. Now, given any collection, which includes lists and strings, those are the 2 kinds of collections that we know about so far, you can find out how many items there are in there by using the len function. All right, so I've got this list m, and I can find out how many items m contains by asking for its len. This will also work with strings. I don't have an s. So if I say s gets hello world, I can now ask for the length of s and be told that there's 13 characters in that string. And this will work for literal lists and strings as well as for lists and strings referred to by variables. So I can ask for the length of 2 comma 4. At least I could if I typed it correctly. Length of 2 comma 4. All right, or the length of hello, and I get what you would expect. All right. Now, any sequence collection, you can ask for slices of that, that is, subsequences of that, by using this colon notation in between the square brackets. All right, so if I have S here containing hello world, or M containing these values here, then M sub 1 gives me one item that is at position sub 1 within that list. But if I say M sub 1 colon 4, let's say, what that means, what that colon tells the Python to do, is to give me a slice of items from the list, starting from position sub 1 and going up to but not including sub 4. Okay, so I colon j means starting from position I, going up to but not including j. And so I colon 4 is going to give me, I'm sorry, 1 colon 4 is going to give me from item sub 1 followed by sub 2, sub 3, but not item sub 4. So I get this sub list 254. No, 25 minus 4, excuse me. Good? I can give another colon and a third parameter here with it, which is a step size. All right, so if I say M sub 1 colon 4 colon 2, then instead of getting a sequence of items that are just one step apart, what I'm going to get is item sub 1, and then I will not get item sub 2 because I have a step size of 2. I will get item sub 3, and then I won't get item sub 4 because item sub 4 is too far anyway. So what I'm going to get now is this sublist 2 comma minus 4. If I were to just say M sub 0 colon, let's see, there's 7 items in this list. I'm not allowed to say M sub 7, correct? There's 7 items in the list, so item sub 7 is too far. But when I ask for a slice, that second subscript is 1 too far anyway. And so in a slice, that works fine. Let me redisplay what M contains, and then we'll say M sub 3 colon 7. I'll get this to work yet. All right, 3 colon 7. All right, and so that means give me from item sub 3 up to, but not including item sub 7, so that's item sub 3, 4, 5, and 6. And if I said something like M sub 1 colon 7 colon 2, I would get every other item starting from item sub 1. So I should get 2 minus 4 and 11. Okay, so does this slicing business make sense, all right? So if you have a list and you ask for a slice, you get a list. Similarly, if you have a string and you ask for a slice, you get a string. So if I say, hello world, sub 2 colon 5, well, I'm going to get items sub 2, 3, and 4, so that's going to be LLO. I'm going to get from item sub 2, which is the first L, up to but not including item sub 5, which would be the comma, and the result here is a string containing LLO. S is a variable referring to hello world, so I could also do a slice of S. All right, so here is S sub 1, 2, and 3, up to but not including S sub 4. So far, so good? Now, it turns out that if you leave out the first index in your slice, Python interprets that to mean item sub 0. Similarly, if you leave out the last item in the slice, Python interprets that to be the length of the sequence. So if I say m, there's the whole m. If I say m sub colon 4, this means give me a slice from item sub 0 up to but not including item sub 4. So I'm going to get sub 0, 1, 2, and 3. I'll get 4 items in my slice. Or going the other direction, if I say m sub, let's say 2 colon, this means give me everything from item sub 2 up to the end, no matter how many items there are in the list. So here I'm going to get a sub list of 5 items. Now, in fact, if you leave both things out, if you leave both the first subscript and the second subscript out, that means to go from 0 up to but not including the length. It ends up giving you a copy of the entire original sequence. All right? All right, now, since plus is used for concatenation, both for lists and for strings, you can use a combination of slicing and concatenating to very flexibly manipulate the values that you have in your list or your string. All right, so here I've got m. Now let's suppose that I wanted to swap the order of these things. I don't want to sort them. I just want to take the last 4 items in this list and put them at the beginning. Well, I can do this by saying m sub, let's see, so the minus 4 is which item? Sub 4? Sub 3, good, yes. So the minus 4 is item sub 3, and I want everything from item sub 3 to the end, so I'll just say m sub 3 colon, and then I'm going to concatenate. How do I get everything up to but not including the minus 4? Colon 2? 3. Good. Okay, so here is how I can take a list and move the end to the beginning and vice versa. I've taken everything from item sub 3 to the end and moved those to the beginning, and then taken the 3 that were at the beginning and moved those to the end. Now this actually didn't change m. M is unaffected. If I wanted to actually change m, I would need to reset m, the variable m, to refer to this modified list. Now m refers to that modified list of 7 items rather than the original list of 7 items that I started with. Make sense? Okay, so we can do the same kind of thing with strings. Here I have hello, and I'm asking for a slice up to but not including the sub 3 item. Okay, so hello. Okay, so what's the sub 3 item here? Well, the sub 3 item, 0, 1, 2. The sub 3 item is the second L, correct? So if I say, give me a slice up to but not including item sub 3, I just get the HEL part. If I do that and append, let's say P exclamation mark, that will get me, the slice HEL, and then append a P and an exclamation mark so that I get this new string help. Now, help is being displayed and then just disappearing. I don't have any variable set up to refer to help, but it would be easy for me to do that. I could just say s2 gets, and then that slice and concatenation, and now s2 is referring to the string help. Here we have another example involving the word international. This is a favorite silly example of mine. I like international because there are so many words that are subsequences within international. We've got the word in, we've got the word turn, we've got the word at, we've got the word ion, we've got the word intern, we've got the word nation. Okay, so there's all kinds of silly trickery editing things that you can do starting from international. And here, if I type 2 colons and a 2, well, 0 is going to be the implied first index, so that's going to start from the I. And the length of S1 is going to be the implied second index, so that's going to go all the way out to the L at the end there. And then what is this colon 2 about? The step size. Yeah, exactly. Good. So what I'm going to get here is every other character from international, starting from the first one and going all the way to the end. So I'm going to get I, T, R, A, etc. It turns out to be I-trainal, which is not a word. But there you go. So you can say, all right, I want to get every other character. And if you wanted to get the odd numbered every other characters, you could just say S1 sub 1 colon 2, and I get Nentawa. Okay, so by using a combination of subscripting and concatenating, I can do more or less arbitrary editing on strings. So if I ask for, if I say give me a t, so to speak, give me a t, and then add to that, let's see, S1 sub colon 8 colon 2. That means give me all of the characters up to but not including character sub 8. Character sub 8 is this I. So give me characters up to but not including 8, but only give me every other one. So I'm going to get the N, E, N. No, I'm not. I'm going to get the I, T, R, A. Okay, so I'm gonna get itra from that, and then let me also add from item sub 7 up to but not including item sub 11. Sorry, this is item sub 7, and so I'm going to get this TION here. And so by foolish magic, I have created the word titration out of parts of this string and added a T. Well, okay, so the point here I'm trying to get at really is that using a combination of slices and concatenation, you have an enormous amount of control over editing lines of text that you might be getting from some kind of input file. If you want to reorganize parts of text lines from a file. Any questions about this slice business? All right, cool. All right, well, it turns out that in Python, virtually everything that exists is considered to be an object. Languages like C++ and Java allow you to do object-oriented programming, but not every single thing in those languages is an object. In Python, literally anything that you can think of to do with Python is, well, now I've just thought of something. Is plus an object? I wonder if plus is an object. Let's find out whether plus is an object. If I ask for the ID of plus, what happens? Oh! So, symbols are not objects. That's cool. But numbers are objects, so I can ask for the ID of 123, and that gives me the unique identifying number for the object 123. So 123 lives in memory someplace and has a unique identifier. If I ask for the ID of 2.7, it has its own unique identifier. If I ask for the ID of hello, that has its own unique identifier. And now what's cool about Python is that data types are actually objects. So I can ask for the ID of int, and it turns out that the int data type does have a complete description stored in memory. And here is the unique ID number of the int data type and of the string data type. Here is the ID number of the ID function. Okay, so functions are objects in Python, and so the ID of ID happens to be that number. Now, you're not intended to be able to deduce anything useful from these particular ID numbers. What Python guarantees is that each unique object in your running Python program has a unique ID number. And you can use the ID function to find out what that ID number is. In fact, if you say something like x gets, well, we can find out what the ID of 7 is. Well, we could if I type correctly. There we go. Okay, so I ask for the ID of 7, and I get this number. Now, it's not the same number as what I had here on slide 39. It's just some unique number. Variables, it turns out, are not objects, but variables refer to objects. So if I say x gets, yes?
So if we restart the shell, then if we again type ID of 7, then will the number change, or is it same for all the...
It may change. There's no, that's an excellent question. There's no guarantee about the consistency of these numbers from one execution of Python to the next. All that's guaranteed is that during a current execution of the Python environment, the Python interpreter, unique objects have unique IDs. If I say x gets 7 and then ask for the ID of x, in this case, I'm not going to get the ID of the variable name x. I'm going to get the ID of the object that x refers to. And since x is referring to 7, I get the same ID number that I got for the constant value 7. Likewise, if I say y gets 7, I'll get the same ID number if I look at the object that y refers to. And if I say z gets x, well, z is not referring to the variable name x. V is referring to the object that x is referring to, which is also the 7. So the ID of z is the same thing as well. Okay? And it turns out that for all small integers, and I always forget whether the range is from 0 to 127 or from 0 to 255, but for small integers, those objects get pre-allocated in memory as soon as you start running Python, and they just stay at that place. So when you say something like w gets 13, Well, 13 is already in memory, and the name W just gets set up to refer to that object that exists in memory. Now, if I say W minus gets 6, well, I'm going to get the value of, remember that that's just the same thing, that's just an abbreviation for saying W gets W minus 6. That's going to take the current value that W refers to, which is 13, and subtract 6 to give me a 7. And then W is going to be changed to refer to 7. And 7 is already in there in memory. And so I get the same ID number now for W that I got previously for all the other variable names that referred to 7. This is a peculiarity of small integers. And it does not apply to floating point numbers, because floating point numbers are a little more a little less simple to search for. And so if I say A gets 1/3, all right, remember one of the rules about Python is when you do division, you always get a float. And that's true whether the two values that you're dividing are both ints or both floats, or one float and one int. So 1/3 is going to be a floating point result. And there it is. And if I ask for the ID of that result, I get this number. If I now say B gets 2/6, well, that's clearly the same value, correct? And if I display it, I see the same representation displayed on my screen. But Python will not search for existing floats that happen to have the same value as one that already exists. I think what I just said didn't make sense, but you probably understood me anyway. It won't look to see whether that particular float already exists. So if I ask for the ID of B, I'm getting a different number than what I got as the ID of A, even though A is equal to B in numerical terms. All right, the double equal sign test in Python means is equal to in the same way that it does in Java and C++. So what does this mean? Well, what it means is that if two objects have the if you look at the IDs of two different things and the IDs match, those things are actually references to the same object. All right, so if I ask for the ID of X and the ID of Y and I get the same number back, that means the variable X and the variable Y refer to the same object. But it's not always the case. It's not always the case that two different variables referring to equal values are going to be the same object. All right, here we have A is not the same object as B, even though A's value is equal to B's value. Make sense? That's the wrong question. Do you understand? It's not clear that it makes sense, but
If you say ID 2 divided by 6, the ID will be the same as the ID of 1 divided by 3.
that's not what happens. Oh, wait a minute. Did you say ID 1/3 like that?
Yes.
And then you said ID of 2/6 like that. Notice that they're not the same. Are they the same for you? They could be. There's no reason that they might. There's no reason that they have to be different. I'm just observing that for me they are different. Okay? And in fact, when I asked for the ID of the computation result 1/3, that number that I got doesn't match the ID for the ID of the object that A refers to that also has the value of 1/3. So I've computed the numerical value 1/3 now 4 ways, and gotten 4 different ID numbers. All right, now it turns out when you create collection objects, even if those collection objects start out containing the same values, they are distinct from each other. They're not the same object. All right, so here I have created a list M, initially containing the values 1, 2, and 3, and the list N, also initially containing the values 1, 2, and 3, but they have different ID numbers. And this is important because it means if I say m dot append 12, m changes, but n does not change. Okay? Or if I say n dot pop 0, then the sub-zero item from n gets popped, but m doesn't get changed. All right, so collections by default are going to be distinct from each other, even if they initially contain the same values. Now, on the other hand, if I say p gets m, now I've said I want the variable p to refer to the same object that the variable m refers to. So now I have 2 variable names, p and m, both referring to the same list. And if I say p dot remove 3, now m has been changed. That same list that m refers to has been changed. I've removed the 3 from that list. Good? Well, so now that we've gotten into the business of wanting to compare values and objects to each other, let's take a list at all of the equality and relational and logical operators that Python provides. And these are going to be similar to what you have available in Java and C++, but with some annoying and important differences. First of all, instead of using an exclamation mark to mean not, we use the word not to mean not. And so that's a, a factoid that doesn't make that much difference. But notice that not also has lower precedence than the equality test and the less than and greater than tests. So that can really trip you up if you aren't expecting it, because in C and C++ and Java, the not operator has the highest precedence of all of these guys. Similarly, in Python, notice that the 2 equality and inequality operators are at exactly the same level of precedence as the less than and greater than operators. Whereas in Java and C++, the relational operators, the less than and greater than operators, have a higher precedence than the equality and inequality tests. Okay, we also have the word and rather than the double ampersand, and the word or rather than the double vertical bar. So we can do all the same things in terms of equality, inequality, relational, and logical comparisons. You just have to get used to this different precedence organization. There's also some things that will work just fine in Python that don't work the same way in C++ and Java. If I say A gets 2.5, B gets 2.7, C gets 2.9, then in Python, if I write the comparison, is A less than B, and is that in turn less than C, this expression, A less than B less than C, has the exact mathematical meaning in Python that you want. It's testing whether A is less than B, which in turn is less than C. And that ends up being true. In C++ or Java, you would have had to write this as A less than B and B less than C, right? You'd have to split it up with an and in between. Certainly this will work in Python, but you don't have to do it that way. Like C++ and Java, evaluation of these relational and logical operators groups from left to right and uses what's called short-circuit evaluation. That is, if you have a long logical test and you can determine quickly whether that whole thing has got to be true or false, then you only do the part of the test that you actually have to do in order to figure out the end result. In other words, let me switch this around. If I say A greater than B greater than C, well, implicitly, that's being evaluated from left to right. A greater than B is being checked first, and then whether B is greater than C is being checked next. But since A is greater than B is false, there's no reason to go on checking anything else, correct? If A greater than B is false, then the whole thing has to be false. And so I don't go on to evaluate C at all. This matters a lot if that thing at the end there is something like a function call. I'm going to jump ahead a bit and let me define a function called foo that returns the same value that C contains. All right, so now if I call this function foo by giving its name and a pair of parentheses, what I get back from it is 2.9. If I say A greater than B greater than foo, well, since A greater than B is false, it doesn't matter whether B is greater than foo or not. So we don't even bother to call foo in this case. And therefore, if foo were having side effects, like writing data out to a file or changing the value of a global variable or something along those lines, none of that would happen because foo is not even called. Make sense? Okay. I didn't mention, but you may have noticed, in this table we also have these words is and is not. Those tests in Python are used for comparing object IDs to each other to determine whether two different variables or expressions do or don't refer to the same object. Whereas the double equal sign and the exclamation mark equal check values. Therefore, if I say x gets 1, let me use floats. I got to use floats. So x gets 1/3, y gets 2/6, z gets x. All right, so now if I ask for the ID of x, I get some value. If I ask for the ID of y, I get some value which is different from the ID of x. If I ask for ID of z, I'd better get the same ID that I have for x, because this assignment here really is just saying z refers to the same value that x refers to. And consequently, if I ask whether x is equal to y, that's true. If I ask whether x is y, that's false. But if I ask whether x is z, that's true. Okay, so you have two ways of comparing for equivalency here. You can compare values using the symbolic double equal or exclamation mark equal, Or you can compare identities. So in other words, if I say ID x equals ID y, that's exactly the same as saying x is y. Good with that? All right. Okay, so here are more examples that of what I just showed, basically. Okay, so now that we know how to do value and identity comparisons and also logical combinations, let's take a look at how to make a decision in a Python program by using if. The only thing to get used to here is that when you write your if test, it has to end with a colon, and then the body of the if in Python is required to be indented. And this is very annoying, but I didn't do this. It's not my fault, so there you go. So if I say if x equals y, colon, the statement that I execute within the if has to be indented one level. Lucky for me, idle does that for me, so I don't have to type the tab key or press the space bar a few times. If you're in a more primitive editor, you'll have to actually make sure that you've typed the correct indentation. So x is equal to y. I'm going to say if x is equal to y, x gets, let's say x plus gets 1. And, okay, so you don't normally type if decisions interactively, but I've done it here just to demonstrate the syntax. X is now 1 1/3 because x was equal to y in value. They were both 1/3 at this point. And so x has now been modified by having 1 added to it. It is therefore no longer the case that x is z, because z is still referring to 1/3. I just changed the variable x to refer to 1 1/3 instead of 1/3. Make sense with the if? All right. In this next example on slide 48, well, let me quickly do the. Let me set a and b up to be. All right, so a gets 12. A gets 12. B, it turns out, gets 12 as the result of this if code on slide 47. All right, so at the beginning of the code on slide 48, I'm asking if A is equal to B, and they are, let's set C equal to -4, and then set B equal to A plus C. So what I'm doing here is I'm creating a variable C within the body of this if statement. If I were to do that in Java or C++, what would be the so-called scope of that C? Which part of the code could I access that C from? Just within the if, right? Or if this were a loop, just within the loop or what have you. So this would be what's called a local variable within that scope bounded by the if. But in Python, when I create C this way, C becomes a global variable, just like A and B are global variables. So this can be surprising if you're not expecting it. All right, so now I have A, B, and C all exist at the global level within my Python environment. It turns out that when you create a variable inside of a function definition, that variable is local to the function. But that's not the case with something like an if decision or with a loop, like a while loop or a for loop that we'll get to shortly. indentation matters greatly, and this will drive you crazy. So if I were to retype this by saying A is equal to B colon C gets minus 4, B gets A plus C, and I accidentally typed a space in there, Python yells at you if any of the statements within a block of code, like here in the body of this if statement, are not perfectly aligned. Even if I say something like D gets 5, and I accidentally typed a space before I typed the D, I get yelled at. So this is it's a feature, okay? And what about this indentation nonsense anyway? Well, Python is unique among popular languages nowadays, I would say, in enforcing this rigid indentation scheme, and a lot of people really don't like it. But there are some good things about it, because basically it means that everybody's code looks the same. Since this indentation stuff is imposed on you, the only flexibility you have is whether you want to use 2 spaces or 4 spaces or 6 spaces, as your level of indentation. You can use 7 or 15 or whatever, but you can only control the level of indentation. You can't control the fact of indentation. Also, you don't have to keep track of matching up pairs of curly braces the way that you would in a C or Java or C++ program. The bad news about this indentation is that the line continuation that you have to use is annoying and clumsy. Typing backslashes at the ends of lines is kind of awful. Also, what if you've got the body of an if that's like 40 lines long? Well, so you just have, you have, let's say, 25 lines of code on your screen. You can tell it's all indented at the same level, but you can't tell just from looking at that whether there's an if above it or what might be going on. Okay, so in that respect, it's handy to have a closing curly brace at the bottom of your if, because then it's really easy to tell where the bottom of the code is. But some things you like, some things you don't like. Such is life. I've been doing all of my examples here interactively within the shell that IDLE gives me by default. But of course, now that I'm starting to do things like if decisions, it's really annoying to type these things interactively. There really kind of isn't much sense in typing things like if decisions interactively. I would be better off using some kind of editor so that I can write some code that's going to potentially last and that I can put in a file. The simplest kind of editor is available in IDLE by saying File, New File. And what I get here is an editor that is barely smarter than Notepad. I mean, this is a really stupid editor, so I don't really recommend it. You're going to be a lot happier with something like Spider or possibly PyCharm. But nevertheless, I can write code in here that will, that will last. So here I've written an assignment statement, S gets hello, followed by S as a statement. And if I say file, save as, let me create myself a new folder called DFP C3 2020. Alright, so now I've got a folder here, and I'm just going to call this S code. Actually, maybe I shouldn't do that. S code is a proprietary language of Goldman Sachs. I think. Anyway, I'll call it S example 1. No! S1. All right, so now we've got this thing called S1, and I can run it by saying run module. And when I run the code, the shell gets restarted, so everything that the shell used to know is forgotten. But for some reason, I'm not getting any output. Well, it turns out that in the interactive shell, if you type the name of an object, the value of that object will be displayed. So if I type the name of the object S in the interactive shell, I get that string displayed by default. But in a program, if I want to see that value of S, I have to use well, there's other things I could do, but the obvious thing to do, the most common thing to do, is use this function called print that knows how to print things onto the user's terminal. So let me say print S instead, and I will now save this. I could say file save, but as a shorthand, common to Windows applications, I'll just say Control S instead. And then, instead of saying run module, notice that I can press F5 instead as a shortcut. So I'll press F5. Okay, and this time the program is executed, and I get the value of S printed onto my terminal. Okay, so now I have a sensible environment in which it's going to make sense for me to type things like decisions and loops and function definitions and so on. And this stuff will now stick around in this s1.py file. So far, so good? Okay. The print function can be given an arbitrary number of arguments separated from each other with commas. And by default, what the print function will do is to display each one of those values with a single space separating them. So if I say print, well, let me say A gets, well, I've already got S, so I'll just say print S, comma, Bob, comma, 11/3, comma, true. When I run this modified code, I should get hello, and then a space where I type the comma, and then Bob, and another space, and then 11/3 and a space, and then true. Let's see if that actually works. So Control S to save, and then S5 to run. Yay, it worked. Okay, so I got hello and a space, Bob and a space, 11/3, and then true. Remember, for floating point numbers, that last digit that you see is highly suspect. It's going to be some kind of round-off error, all right? So we're seeing a 5 there as opposed to a 6 or a 7, which would make more sense. The print function also makes use of some so-called keyword arguments that you can use to modify the default field separation and also the default end-of-line character. When I ran print, let's see the output here, I didn't say this, but when I got to the end of printing hello, print automatically adds a new line character so that the next line starts, so that the next output starts on the next line down. All right, so I got hello and then a new line, and I got hello Bob 11/3 true and then a new line. I can use keyword arguments to modify the separation or the line end. If I say sep equals comma, now instead of having a space as the separator between these output values, I'm going to get a comma as my output separator instead. So let's try that. So I'll say Control S and F5, and yes, so in this in this version of print here, I got commas between the argument values rather than spaces. You're not limited to having that be just one character. I can have that be some arbitrary string. So let me use, for example, a horizontal tab in here as my separator. All right, \n is a newline character. \t is a horizontal tab character. And so now each of the output here is concluded by a horizontal tab. And I can even, if I would like, have the output field separator be a new line. So now I'm going to get hello and then a new line and Bob and a new line and 11/3 and so on. All right, so I've got my 4 values on separate lines by using a new line as my separator. So far, so good. Okay, we took a look at some very simple ifs. Commonly, an if has an else part associated with it. So you say, if something is true, I'm going to do this block of code. Else, if it's not true, I'm going to do this other block of code. And in fact, it's also common to have several so-called elif clauses in between the initial if and the final else. Elif is just an abbreviation of else if. So in here I could say, A equals 12, B equals 17, C equals 5, and then if A is greater than 9, well, that's not going to be very interesting because A is greater than 9. But, if A is greater than 9, print A is greater than 9. Elif A is less than 9, do something else. I'm just going to type some junk in there. And else at the end, do some third thing. Now, the only thing I want to point out here, because I always make a mistake myself, is that each of these decision points, including the else, has to end with a colon. And, despite how long I've been writing this stuff, I'm an old-time C++ programmer, and so I always forget the colon at the end of the else, every single time. But you do have to have a colon there, just like you do at the end of your if and the end of your elif. So far, so good? Okay. I just don't want to get yelled at here, so let me say print A and print B, so that I just have some valid syntax in here if I run this thing again. Well, so now we know how to make decisions. If we want to have something occur repeatedly, we're going to need some form of loop. And there are a couple of different forms of loop available in Python. First, we have the while loop, which has the same general form as an if, except that the body of code is going to happen repeatedly as long as that Boolean expression at the top remains true. Okay, so while this Boolean expression is true, then perform the body of code, which are these statements that all have to be indented at the same level. Let me go ahead and just type this one in interactively. I can do that, although it's not really very normal. It's common with a while loop to start out with some kind of loop variable that you have to initialize properly. So I'm going to create this loop variable I, initialized to 0, and I will then say while I is less than 10, and a colon. Idle conveniently indents an appropriate amount. I'm going to do something really simple here. I'm just going to print out the current value of I. And at this point, a popular thing to do, even for me, is to just hit the enter key, and then you accidentally have created an infinite loop because i's value is never changing, and so it just prints 0 forever and ever. We want to remember to modify I so that eventually it will become 10. So I can say I plus gets 1. And now when I hit the enter key, okay, the first time through the loop, let me grow this a little more. Okay, so the first time through the loop, i's value was 0. And since 0 is less than 10, I printed the 0 and increased the 0 to a 1. Well, 1 is still less than 10, so I print the 1. Eventually, I get up to I being 10, and at that point, the loop is over. The upshot is I will have printed 10 lines of output with values from 0 through 9, but not including 10. Okay? If you've ever written code in your life, that's not a surprise. So far, so good? Question? No. Yes? No. Okay. A much more common kind of loop in Python, because it's used for iterating through collections of things. Whoops. Sorry. I hit the end key rather than the page down. All right. A much more common kind of loop is this thing called the for loop. And the for loop sets the value of some variable whose name you just pick out of thin air, one value at a time, to each of the values in some so-called iterable. Now, an iterable is a thing that you can iterate through. It's a thing that you're allowed to step through with a loop. A list is one example of a so-called iterable. And if you iterate through a list, you get back the first value the first time through, and then the second value, and the third value, etc. So let me try this one. I'm going to say for I in a list of values 2, 4, minus 3, 12, 99, 22 would have been fine, but it had to be 99. So I is going to take on the value 2 first, and then 4, and then minus 3, and so on. And what I'm going to do is I'm going to print out the value of I, followed by a tab, let's say, and then followed by I squared. All right? So I get I get one line of output for each value in the list. 2 and 2 squared, 4 and 4 squared, minus 3 and minus 3 squared, etc. Good? Just as a list can be iterated through or stepped through, likewise a string can be iterated or stepped through. And what happens here is that we're iterating through the string one character position at a time. Now, in Java and C++, we have a character type, right, that holds a single character, which is different from the idea of a string. Python only has strings. It doesn't have a separate character type. What's happening here when I'm looping through this string with my for loop is I'm getting the one character wide substrings from that original string one at a time. So if I say for C in hello, if I say print C and the type of C is type C, All right, so the first time through, this variable c is going to be set to the one character string h. The next time through, the variable c is going to be set to the one character string e, and then the one character string l, and so forth. So this loop is going to go through 5 times, and I'll be told h, and the type of c is stir. Okay, e, the type of c is stir. So in each case, the value that I get in my variable c is actually a string, but it's a string that's one character wide. In fact, let me expand on this even more, because I can say with length good. Now, another form of iterable that's not a collection is a function named range. I can say for I in range 10, and what's going to happen is that this range function is going to give values back to me, one value at a time. The first value I'll get will be a 0, and then I'll get a 1, and I'll get sequential integers starting from 0 up to but not including 10. Okay, so when I say range 10, what I'm really meaning is the integer values from 0 up to 9. And I'll just print these guys out. There we go. Remember that I can modify the... well, I showed you that I can modify the separator in a print, but let me also show you that I can modify the end of print as well. The default end of print, no, I can't get it to behave. The default end for a print is new line, because by default print adds a new line to the end of the output. But if I say display I and then have an end equal to space instead, this will enable me to get all of the output on a single line with spaces between the values. If I specify 2 arguments to range, then the first argument is where to start, and the second argument is one beyond the end. All right, so I can say for I in range 10, 20, and that means to go from 10 up to 19. And I can also specify a step size. So this is very similar to the idea of a slice, except that we are using this to loop through items in a range of values. Okay, so the range function gives you tremendous flexibility for specifying a range of integer values that you want to step through in something like a for loop. You can also go in a downward direction. You can loop in a negative direction by setting -1 as your step size. Right? So if I say for I in range from 4 down to 0 with a step size of -1, I should say down to but not including 0. So actually, let me say -1, print I. So this range is going to start at 4. When we hit -1, the for loop will end, and -1 will not be used for anything within the for loop. My step size is -1, so this should display 4, 3, 2, 1, 0, and once I've hit 0, that's it. Questions? Okay, So now we know about variables, we know about object identity, we know about the fundamental data types. We can create lists of things, we can interact with strings of things. We know about how to access slices of things like lists and strings. And we've seen how to do equality, relational, and logical operations, which in turn we can use in decisions, if, else, and the while loop. And we also know about using the for loop to step through some sequence of values. Either a sequence of values pulled out of an iterable object, like a list or a string, or from a range of integer values. Wow, I'm so impressed with myself. It's exactly 20 after 4. It's 4:21 now. Okay, so we didn't quite make it to modules. We'll pick up these last couple of items on Tuesday. Okie doke, so I'll see you then. Have a good weekend.